This is a recording of a webinar presented by Dr. Susan Murphy of Harvard University on September 6, 2018. This is the second of two webinars on micro-randomized trials presented by Susan.
Okay, thanks. It's great to be here. Now, remember we already did one webinar on the micro-randomized trial. And what I'll do is I'll give you a little bit of a review of that webinar, but if you're watching this offline at a later date, you might want to look at that webinar first before you go to this one. It'll make everything much clearer. So today what we're talking about is how, if we've already run a micro-randomized trial, what are some of the primary and secondary analyses that we might be interested in, and how would we conduct those analyses? So here you see exactly what I just said. Our goals are to better understand what these analyses might be, what these aims might be, and then present a method for addressing these aims. So what I'll do is I'll start off with reviewing the structure of the kinds of data we're going to be seeing after we would run a micro-randomized trial. So essentially you see at the top of the screen, I'm not sure if you can see my mouse. Can they see my mouse? Ashley? No. Okay, so at the top of the screen, there's a row of variables, and this is what you would get from each individual, each participant in the study. X is the data that accrues between the time points. The subscripts, that's T, that's the decision times. And remember in hard steps, these decision times were 5 times a day associated with a person's work schedule. So XT is the data that accrues between that, both self-report as well as sensor data. IT, which first we have XT, so you think of that order is the order in which you would observe data. First, the data that accrues up to time point T. Then IT, that's an indicator variable of 1 or 0, and it's whether or not that participant, that individual, is available for treatment intervention at that decision point. So in hard steps, what we discussed before was, for example, if the person was currently detected to be walking, then they would not be considered available for treatment. And the reason why was because the kinds of messages that we're providing in hard steps are messages about new types of walking activities. And we didn't really want to bother someone. If they're currently walking, we don't want to say, oh, stop what you're doing now and undertake a new kind of activity. Now, of course, if our suggestions were about extending one's current activity, availability might be defined differently. But no matter what, we always observe availability prior to sending any kind of message. And AT, that's whether or not, it's an indicator as well, and in the simplest cases, and you see here on the screen, it's coded as 1 if an activity suggestion is sent, 0 otherwise. And these activity suggestions are randomized. And in all micro-randomized studies, they're randomized with probabilities that we know about. And in hard steps, when we were first designing hard steps, we thought, well, there's 5 times a day. We wanted about an average of twice per day that we would provide a suggestion, so we used a randomization probability of 0.4. Now, we're hoping that these activity suggestions, they're contextually tailored activity suggestions. Our goal is that they'll be useful in the near time for that individual. So that's why we focused on the next 30 minutes. Now, we would love this if the person remembered these messages at other times of the day and utilized the ideas. But because they're contextually tailored to the setting of the individual, the weather outside, where the person is, they're most actionable over the next 30 minutes. That's why our proximal outcome is step count over the next 30 minutes. Here's a little schematic. Actually, Erin made this little schematic. Thank you to Erin. And you can see at the top row concerns these activity suggestions, with on the far left the observations, the kinds of observations, then the gray triangles assessing availability, the green circle is the randomization, and then the proximal outcome, which in our case is the 30-minute step count after a decision time. Remember again, 5 times a day. This is a 42-day study. So if someone were available at all 5 times every single day, they would be randomized 5 times 42, which is 210 times. Again, you see at the top the series of data that you would get on each individual and just some reminders of what that data is. So when we were thinking about this study, we had 2 main questions. First of all, is there anything going on at all? I mean, do these contextually tailored activity suggestions, do they really impact people's behavior, their step count? And then because these suggestions are reminders in which we interrupt the person's life in order to provide support, we realize that there could be iatrogenic effects. That is, we could cause burden to the participant, and the participant might start to disengage. So a big question for us, a second question was, if there is an effect at all, does it decrease with time and study? In the 1-and-1 on micro-randomized trials, we defined the main effect, and that's the primary analysis concerns this main effect. And here you see it written down. I denoted it using beta of t. So that's what we could think of as the effect at time t. So it's the mean 30-minute step count given the person is available and they got treatment, minus the mean 30-minute step count given the person is available and they were not randomized to treatment. And as you can well imagine, this beta of t may change with t, so it's time varying. It's a causal effect, mainly because we randomized AT, the indicator of treatment. And it's a causal effect among the people who are available at time t. I just want to review to be really clear about what this effect is, and that's what the next slide is going to be about. So in this next slide, I just rewrote what the definition of the effect at time t is, this beta of t. And then I asked myself, well, what does this mean? And when we were thinking about the study, I drew this little rough curve. You notice the horizontal axis has 210 decision points on it because that's the 42 days, 5 times a day. And then the vertical axis has standardized effect sizes. And we were thinking at the very beginning that when someone first enrolls in the trial, they'll be a little confused, so there may not be much of an effect at first. But then as time goes on, they'll get suggestions and they'll try them out. If they don't get a suggestion, they won't try them out. And so we might get an effect as time went on. But then, because we are intruding in their life, we may end up seeing a decrease in the effectiveness of these messages, at least in terms of their subsequent 30-minute step count. And that's why that curvilinear, that quadratic term starts to turn down. It was because we were so very worried about that decreasing effect with time. One could think that might be due to habituation, for example. If I'm constantly being reminded to do something or I constantly receive a suggestion, I might eventually just not even see the suggestion. So it'll have less and less of an impact on me because I habituate to that message. That's what our main concern was. I just want to make sure we're all on the same page. There's another reason why this beta of t may vary over time. Let's think about it's only among, at any given time point, decision time, this is an effect that's among the participants who are available at that time. So suppose some group of people really start to engage with these suggestions. And they experience a positive habituation in the sense that they start to incorporate walking around these 5 times of the day related to their employment. Then they won't be available because they'll be walking at the decision time. So the people that are still available to be randomized as time goes on would be the people who are, in some sense, you could view them as the most treatment resistant. So in that case, you might expect to see a decreasing effect of the message or this activity suggestion, because at each given time, the subpopulation of people who are being experimented on are the more and more treatment resistant. They're the people who are currently not walking. Now, I have to warn you, in Heart Steps, it was a smaller study, and we didn't see any evidence of this type of an impact. But in a very large study, we might very well see that, and so I want to always keep that in my mind when I think about analyzing micro-randomized trial data, certainly when I start doing tertiary and hypothesis-generating analyses. Okay, so now we have some understanding of what our main effect is, and we're going to go on to how we think about testing whether or not it could just be equal to 0. We could have no effect whatsoever. We really want to know, is there a signal? So that's what this slide's about. I just wrote again the stream of data you'd see on any one participant at the top, and then the definition of the effect right below that. And then I said, well, what is our primary hypothesis? And of course, as you well know, the primary hypothesis is how you determine your sample size and thus the budget for whatever trial, in this case a micro-randomized trial, that you would propose. And because we were so concerned about that chance of negative habituation, a decreasing impact with time, we decided to focus our alternative hypothesis to really maximize the power for a quadratic trend. Now, of course, in reality, we know that any real pattern will not be quadratic. This is extremely coarse, but we wanted to detect the potential for a deteriorating effect, mainly because we were so very concerned about that. So this is how we sized the study, and we discussed this in 1N1 on micro-randomized trials. So I'm just being a little repetitive to help me be clear. So we chose a quadratic alternative with time to focus on, but one could have chosen a linear. None of these are going to truly fit the underlying pattern of beta of t as time goes on. The goal is to capture enough so that we would have adequate power to, in our case, detect the decreasing effect. Actually, right now on this picture, it looks really good, because here it's like we had an increasing effect, but in reality, I was very concerned about a decreasing effect. So the linear would be sloped down rather than up. Okay, so what happened when we got ready to run that micro-randomized trial? We're using we developed an app, a mobile app, and that involves a lot of coding, as you can imagine. So what we did was we ran a small pilot just to test our software. And what we learned was that the participants were unavailable around 20% of the time. So available around 80% of the time. That is around 4 of the 5 times per day. And we became worried that, well, then they're probably not going to get around 2 messages per day. So we decided to increase the randomization probability from 0.4 to 0.6. And that's what you're going to see me when, this was before the actual study was started. We recoded the software to increase the randomization probability to 0.6. And we made another decision, because we saw this only 80% availability with this early group of individuals, we decided, look, let's not waste the degree of freedom to get a quadratic for our alternative. We'll just go for a linear. It only uses 2 degrees of freedom. We'll have more power. So our alternative for the null is going to be a linear. And this was all decided before the actual study went into the field. It was a consequence of doing that feasibility pilot for testing the code. So this is how we're going to go from now on. So now we're ready to talk about the method that one could use, and this is all going to be illustrated using the HeartStep study. Just to remind people, again, the HeartStep study is a physical activity study, like we saw in that schematic, and we're going to be focusing on these contextually tailored activity suggestions that could occur at any of the 5 times a day over the 42 days. So these are the questions, we've stated them before, and then you see the data, the coding of variables below that. Notice DT there, it's the third variable that's listed. It codes day and study. And we coded it so the first day, DT for day 1 is equal to 0. So DT only goes from 0 to 41. It's equal to 41 on the 42nd day of the study. And we'll also be using summaries of the kinds of data, of the data we're collecting, and we'll call that ZT as we go through this discussion. So how might we address these questions? And you can imagine, you can think about it from a conceptual point of view, at least at first, just to get our thoughts in order. So that's what I'm going to be doing right now. So from a conceptual point of view, I would think, well, I really want the first analysis is whether or not there's any kind of signal at all. That might be that first conceptual model at the top. And in red, remember AT is 1 if they get the activity suggestion, 0 otherwise. So beta 0, it indicates to me the effect, the average sort of effect. And I'm going to talk about that as we go through. So let's focus on that beta 0. So what is the interpretation when we're first even thinking about this problem? Well, we know that beta 0 represents an average type or marginal effect. I mean, we didn't include gender in this analysis, this model. We didn't include the day of the week, whether they were at home or work, time of day. All of these different kinds of contextual variables or attributes of the individual could impact how responsive they are. In fact, there could be things that we didn't even observe that might impact their responsivity. But that first analysis doesn't really concern that. It's just, is there a signal? So that's why you have this interpretation. We recognize the marginality of this beta 0. But it is causal. It's a causal effect because AT is randomized. 60% of the available people, 60% are randomized to AT equal 1, and 40% are randomized to AT equal 0. Then if we go to a second analysis, this is where we're really starting to get concerned with that decrease of effectiveness with time. Here again, we include our DT, which is 0 on the first day of the study, all the way to 41 on the last day of the study. So that means because D of T is 0 on the first day of the study, the coefficient beta 0 really represents early impact of the message on the subsequent 30-minute step count. And it's still marginal, though, because I didn't include gender. I didn't include whether it was a weekday or a weekend. We didn't include weather, time of day, and so on. It's still marginal, but it's causal because we randomized. We know it's going to be causal. We have approximate compositional equivalence between the 60% that got AT equal 1 and the 40% of people who got AT equal 0. So we know we have a causal contrast, but it is marginal because we didn't include all these characteristics, both of the individual and the current situation they're in. Now, the beta 1 tells us about how the effect may change with day and study. So given my concerns, the concerns our team had about how this intervention because we're interrupting the person in their daily life, and thus they might start to habituate or disengage. If beta 0 is positive, I get a positive effect early in the study. What might you think the sign of beta 1 would be? And what do you think we were concerned about? Well, I thought, well, man, this beta 1's going to be negative. I'm really worried it's going to be negative. And why? Because I'm concerned that as time goes on, we're likely to see a deterioration of the effect of the activity suggestion. And we're concerned about habituation. People just don't see the message after a while. Now let's go to the other part of our conceptual model. This is the blue part. And we always do this when we analyze experimental data in which we have randomization. We always recognize that these are human subject studies, and there's enormous noise. All kinds of things are going on in people's life. And so if there's some way that we can control or reduce the noise, the residual noise in our outcome, that will help us see a signal. It's all about increasing the signal-to-noise ratio, increasing the power of our tests, reducing the width of our confidence intervals. So in most studies, like if you go to a lot of health studies, we always use a pre-treatment measure of, for example, like how severe the disorder is as a control variable. In educational settings, if you're looking at a treatment designed to improve reading, you might use the participants' pre-treatment reading ability as the ZT, as the control variable, since the YT plus 1 will be their post-treatment reading ability. So in fact, those are the very best control variables. If you can get a pre-treatment measure of the outcome, that's really what you want to do. That really reduces the residual noise. And in fact, we're able to do this here in Hard Steps. You're going to see us do this. Now, from a domain or a scientific perspective, our primary focus is really not on the alphas. The real role of these control variables is to increase power so that we can detect whether or not our activity messages are impacting individuals. So when we go to think about how we might analyze this data, whatever method we use, we want to have a method which still provides that same understanding that I just went through. That is that these regression coefficients, these betas, they are causal. They do have a marginal meaning because we're never able to include all characteristics of the individual. We didn't even measure all characteristics, so it's always marginal over those characteristics. But it is causal. So we want to make sure whatever we do, we can still have that content, that scientific content. And in order to have that, there are some real challenges. And one of the big challenges is the treatment is time varying. At each of the time points, a person either gets treated or not. They either get a message, an activity suggestion or not. We can have increasing habituation. They may not be available because of how they responded to past treatment and so on. All of this creates this endogeneity or this feedback loop. And that's exactly what this last bullet point says, is that your controls and any moderators you might be interested in, they may be outcomes of prior treatment. In particular, availability, IT. Remember, IT equal 1 if they're available at time t to be randomized. IT equals 0 if they're not available. That could definitely be impacted by prior treatment. So we have to analyze this data in a way which allows us to extract the causal effect, but not somehow accidentally pick up that feedback loop and bias our causal effects. It turns out, amazingly, at least it was amazing to me as we went through this, the process of developing the method. I actually thought originally the method was going to be really complex. And it turned out that it turned out to not be very complex at all. It was quite interesting, and you're going to see that on the next slides. So it's a very simple method, even though the data, at least at first glance, appears quite complex. I realized this actually in some prior talks I have given before, is that when you play a strong role in designing a study, an experimental role, often the analyses are very simple. Complex analyses usually have to be used in more observational settings. Here, because we're able to design these studies, we're able to use, at least for the primary analyses, very simple methods. And you see some of the aspects, a little advertisement for the simple method. Easiness, it's versatile. We're able to incorporate control variables to reduce noise, and we're able to incorporate these control variables in a way that doesn't bias the causal effect. Now, this is a big deal. This is particularly the case here because the number of control variables one has at hand, say by time 150, is quite large, and it's difficult to imagine you're going to really get a true model for the outcome of 30-minute step count. There's a paper, I'll give you a reference here. Actually, if you go to the Journal of American Statistical Association, it's online. They put this online before it appears in print. We're really fortunate because in Hard Steps really helps me explain this analysis approach, because in Hard Steps, all the randomization probabilities are constant. They're equal to 0.6. And as a result, the analysis method becomes really simple, and that's the analysis method we're going to use today. But I'll give you a link to software that Danny Almirall wrote, which allows you to analyze micro-randomized trials in which the randomization probabilities are not constant. And in fact, they can depend on the pattern of the individual's past data. Okay, so the first analysis we wanted to ask in Hard Steps was, is it worthwhile to provide a contextually tailored activity suggestion? And you see those randomization probabilities there, 60% of the time. If they're available, we randomize them to get the contextually tailored activity suggestion. 37 participants, this was sized to test this particular alternative. Here's our conceptual models. Again, I didn't emphasize this before, but I do want to emphasize we shouldn't view these as models, data analytic models, in the sense that we're trying to really model how y(t+1) evolves through time. That's not what's going on here. We're constructing these models to detect whether or not there's a signal. Again, the conceptual model, we actually used a log transform step count. The 30-minute step counts, they're very skewed, and the log helps us make the distribution of step count much more symmetric, and thus our p-values and our confidence intervals are more accurate. That's the reason why we're using the log transform. Notice what we use to control the control variable. Yeah, our outcome is this log transform step count in the 30 minutes after the decision point. Our control variable is the pre-treatment 30 minutes, that is the 30-minute step count prior to the decision point. Highly correlated, and this was pre-specified, and it works like a charm because ZT and YT+1 are so very highly correlated. Again, DT is coded, so DT equals 0 on the first day of the study. So here's how the data might look to you. Each row is a person period. So there is for every day, there's 5 rows for a person, and then of course you go across the 42 days. So as you can imagine, so now you have 210 rows for each person. And you can see that for person 1, the second column goes from 1 to 210. And then the third column is about the coding of the day. So the first day, the first 5 decision points are all about day 1, which is coded as 0, and so on and so forth. And then at each one of those decision times, we know before we even randomize whether or not they're available. And so in this little fake data diagram, we see that on the first day, the morning for the first person, they were available at that time. That's the 4th column. The 1 indicates availability. And then the 5th column indicates that that person was randomized to receive an activity suggestion. 234 is their step count prior to that randomization, and 316 is their step count after that randomization. And it just continues down through the rows, 210 rows for every single participant, all 37 participants. So it's a very long data matrix, as you can imagine. Here's the code. This is using, it turns out, because we have a constant randomization probability, we can use the code corresponding to generalized estimating equations. This is not quite a generalized estimating equation. We're tricking the software to do this, to fit these kind of conceptual models. So it's great. So here you see us using GEEPAC with the code that one would use in this case. Weights, the weight row is, we just put availability there. It's an indicator of 1 or 0 whether the person is available. The standard errors are always robust standard errors. That's absolutely critical because we all know that their within a person, step count must be correlated over time. So you need to use robust standard errors. I'm going to talk a little bit about that later. Here, when we trick the GEE method to analyze this data and give us those beta 0 and beta 1 estimators, we use what's called a working independence correlation matrix. And this all has to do with ensuring that we get causal effect estimates. And we'll talk about that shortly too, but I just want to continue on. So the first run of the GEE GLM is for the top conceptual model. The second run of the GEE GLM is for the second conceptual model. And like I said, you can use this particular software. This is our code, right, Ashley? Mm-hmm. Yeah. You can use this software as long as your randomization probabilities are constants, like they are in hard steps, where they're equal to 0.6 to be randomized to get a message, 0.4 to not get a message. Here it goes again. Oh, yes, this is exactly what I just said. I'm just repeating myself. I wanted to make sure I did it. This is a very special case. You get this great implementation because in hard steps, the randomization probabilities are constant. It turns out most of our most recent MRTs do not have constant randomization probabilities, and we do have to use a code that Danny wrote, and I'll give you a link to for those settings. Okay, that's the code. Let's see what happens when we apply this to the data set of 37 people for hard steps. So here's that first analysis. I put in blue the parts of the analysis that I really care about. So beta 0 with that little prime thing to indicate, it's estimated at 0.13. Now that's on the log scale. Remember why it's log step count. So to even interpret that, I have to provide, calculate that. And I wrote down a note for myself. 0.13, it corresponds to about a 14% increase in step count. So with these people, the people who were in this study, we only recruited relatively sedentary people. They were getting around these 5 times a day. They would usually get around 250 steps. So 0.13 represents about a 14% increase in their step count, around 33 more steps over the usual 250. So that's the primary analysis, and then we went to the analysis involving day in study. And remember how concerned our team was about deteriorating effects. And in fact, when you look at this analysis, you see that we were right to be concerned. So let's first focus on beta hat 0. It's 0.51. How do I interpret that? Well, I know DT is 0 the first day of the study. So beta 0 represents the treatment effect very early in the study, the first day of the study, right around the first day. And 0.51 on the log scale, what it represents is around a 67% increase in steps over the usual 250. This is around 170 steps. So this is already quite a nice effect. Unfortunately, you see that second coefficient, beta hat 1, it's, like I said, it's just exactly what, it's depressing. It's exactly what we thought. We get a negative coefficient. It looks like it's really small, only minus 0.02, so you'd think, oh, maybe not such a big deal, right? But the issue here is, it's 5 times a day. By the midway through the study, 42-day study, so around day 20, 21, that negative slope there it killed it. So by around midway through the study, we're not seeing an effect of the intervention. And I have a little graph. Ashley made this figure for me, which really helps people see this. So the black jagged line, so first of all, the horizontal axis is the day in study. It's a 42-day study. It goes from 0 to 41, because that's the coding. And then the vertical axis is the treatment effect estimate. So we're just focusing on the treatment effect here. And the black jagged line is just the average treatment effect on each day of the study. And as you can see, this is really noisy data, as one might very well expect. And then you see different, what's called low S estimators, smoothed estimators of the trend, depending on how much you smooth it. If you smooth a lot, you get the blue, a little less, you get the red, and you can really see that decreasing trend. And then you see the green, which is we use the green line to form our test statistic for our alternative hypothesis. Now, this is not a linear, it's grossly a linear trend, right? So that gross linear trend is enough to pick up the signal that, unfortunately, the effect of the suggestion is deteriorating with time. Again, this is another reminder. I put this slide in so I would make sure I said this. This was a pre-planned hypothesis test of no effect versus an alternative. And the alternative is based on projecting the true time-varying treatment effect, which is sort of like that black line, onto a linear line, and that green line is our linear line. And certainly you're not going to say, oh, the green line is a best fit data analysis. This is not an observational data analysis. This is pre-planned. It's for an experimental study. And we're trying to pick up the main signals. And that's what's going on here. And that's what you saw in the last analysis. So it turns out in Heart Steps, it's a very interesting study because we actually had 2 variants of the contextually tailored activity suggestion. The first variant was a walking activity suggestion, and this took about 3 minutes to enact. It's a little bit of a burdensome suggestion because you are being interrupted in your daily life. That's why it's burdensome, even though it only takes about 3 minutes. And the second variant was an anti-sedentary message. I like that message a lot. An example of that kind of a message was, why don't you stand up and roll your arms in your neck? So it was really nice for me. It made me feel really good, but it certainly didn't take 3 minutes to enact. So we wanted to know, one thought was, well, if we can just get you to stand up, maybe you'll start walking. Maybe if we can just get you going. Or do we have to give you a more burdensome message the 3-minute message, which is the first type, the walking activity suggestion. So now you're going to see how we start to look at that. And of course, when we analyze this, the primary analysis for this contrast, we're going to have 2 indicators of treatment, an A with a subscript of 1 and an A with a subscript of 2, because we have 2 different kinds of treatment. There you see it. The subscript of 1 is the walking, the more burdensome activity suggestion. Subscript of 2 is the less burdensome. Now the data matrix becomes wider because you need 2 indicators of walking and sedentary. And you see that in the 4th to the last column and the 3rd to the last column. You see those 2 indicators of whether or not a message was a walking message or an anti-sedentary message. The analysis, here's the GLM code for this analysis, again, using robust standard errors to form your test statistics and your confidence intervals. The results. So here the result is whether or not, okay, so you see at the beginning it looks like we have an impact of the walking, the more burdensome messages versus no message at all. That actually, 0.21 translates to about a 23%, around 60 steps more per 30 in the next 30 minutes. Unfortunately, our anti-sedentary or sedentary reducing messages, they just didn't pan out. So we didn't really activate people to move. It didn't work, even though participants really liked this in exit interviews, but it didn't seem to activate them. We also, of course, we were really concerned about deteriorating effects with time, so we interacted all of this with day in the study. So I'd just like to focus your attention on the first analysis and the first estimator, beta hat 0, and the 3rd estimator, beta hat 2. There again, we see an initial effect of about 0.729. Now, what does that translate? Remember, we're on the log scale, so 0.729. That's about, this is a really great effect. It's about 107% increase, almost over a doubling of their steps early in the study if they get a message versus if they don't. But again, you get that negative slope. That's that 3rd line in this table. And again, by midway through the study, it's gone. This is really interesting, actually, because we are going to have a Heart Steps version 2 that's going to go in the field pretty soon. And we're actually there, instead of the randomization probabilities being 0.6 and 0.4, we have an algorithm that's running that's going to back off, reduce the probability of providing an activity suggestion if the effect starts to deteriorate. And the idea is if we can get people to dishabituate, then maybe they'll be able to once again benefit from the messages. And it's all because of this analysis. So here's a little graph. It's very similar to the one before. You see how that green line, which is that linear fit, it's just picking up this gross deterioration with time. No one would say that this is a perfect model. This is not an observational. This is not a model fitting exercise. This is a secondary analysis in an experimental study. There's the one with our anti-sedentary messages that I loved. Yeah, right. You see it, maybe you think there might be a deteriorating effect, but nothing is significant here. It's quite depressing. Right, Ashley? Mm-hmm. It's very depressing. Let's not discuss that, okay? We'll go into different kinds of discussion. So if the randomization probabilities you're using depend on the individual's data, which is exactly going to be the case with Heart Steps, the next Heart Steps, then one has to use a more general method. And luckily for us, Danny Amaral has written really nice code to do that, and I give you the link here. And another great thing about this code is it uses a number of small sample adjustments. And so that means that the the confidence intervals are more accurate. And why do we need small sample adjustments here? It's because when you form your alternative hypothesis by using a low-dimensional alternative hypothesis, in this case linear or quadratic, you're able to use both between-person contrasts as well as within-person contrasts. This means you can use smaller sample sizes, and you really do need these small sample adjustments. That's absolutely critical here, and his code includes all of that, which is quite nice. Now, this is a sad reality. Probably many of you noticed that when I talked about this, using the generalized estimating equation, I said you had to use a working independence matrix. Now, of course, we're not really fitting the mean of YT, step count, over time. That's not what's really going on here. We're just modeling the treatment effect, not the mean of Y given the past. That's first of all. The second point is that we ended up using this working independence correlation matrix, even though we know full well that step count has got to be correlated over time within a person. But why are we doing this? Because we want to ensure that our causal effects we're estimating are unbiased. And what happens is when you use off-diagonal elements in your correlation matrix, GE, which was not intended to be used for this type of a problem in which you have time-varying treatment, what it does is it uses future data to estimate present treatment effect. That, of course, we know is a big no-no in the causal inference world, and you end up with biases. And Danny did this really nice simulation. This simulation actually illustrates two issues, but I'll just show you the simulation so you can see this. Here's a real generative model here. It's got an error term, and I accidentally deleted it. Oh, please forgive me. Danny will kill me. I'll fix these notes before I put them in. At the end of that YT equals blah, 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 it should be plus error T plus 1 there. And the error is a normal 0, 1. I must have just deleted it when I was editing these slides. And these errors have a autoregressive pattern. That's where it says the correlation between the error, the residual at time t, and the residual at time u has this pattern. And in this real simple case, people are always available because we wanted to make it really clear. And our goal at first was just to say, well, let's just estimate the marginal effect of treatment. And you can tell the marginal effect of AT is minus 0.2 in this little pretend study, pretend analysis. And here the randomization probabilities are 1/2. Now, there's two ways we could analyze this. We could try to somehow take into account the fact that we know that the outcome Y has residuals which are correlated within a person across time. Or we could use the approach we've given to you. Again, I left off my error term. It's really quite appalling. Again, so we're going to fit. See at the very bottom, you see what we're going to fit. But we're going to use it either an independent or an AR1 working correlation structure here. And what you see when you do that is that our method, which is the top row, the mean is indeed the right treatment. It's unbiased. It's exactly minus 0.2. That's just a fluke. But we expected it to be close to minus 0.2 because the true value of beta 0 is minus 0.2. And then the confidence, we were forming 95% confidence intervals, so we wanted confidence level of 0.95 for this data set of 30 individuals, 30 time points, and you see the confidence level is 0.96, so that's pretty good. But then when we tried to take advantage of that AR1 correlation, everything went down the tubes. And that happened in these settings because AT is randomized. you're not getting misfit due to how you're controlling. It's really due to the fact that ST here is endogenous. It's impacted by prior treatment. I wanted to give you a list of the collaborators. Peja, he works in human-computer interaction. He was the PI of Heart Steps. Danny, he's the guy that did the nice coding that I gave you a link to. Audrey was also involved in producing that code. Nick was a whiz with the Heart Steps data. I don't know what we'd do if we didn't have Nick. And Ashley and I, along with Danny, put together this one-and-one. Thanks.
Okay, I'll scoot into
Do you
the
want to
frame
get
now.
into my frame?
Not lurk behind it anymore. Thank you, Susan. That was wonderful. So I am Ashley. I'm going to take us into the question and answer hour of this one-on-one. But before I do that, I wanted to give participants time, if they still have questions they want to type up, to send them in. So if you have a question, you can type it into the chat section of Zoom, and we'll give Susan a few minutes, and then we'll start the question and answer.
How long will we wait?
Just about 2 minutes.
2 minutes?
Yeah.
Okay.
I think that's good. Should we sit down? Okay, and so if you end up having some questions during the session, feel free to type it in the chat section, and I'll continue to ask Susan. So the first question I have for you, Susan, is how would you assess interactions between intervention components operating at different time scales?
So a lot of people began to recognize that even though an activity suggestion, for example, Heart Steps, it was designed to be really useful over in the near time because the content of these activity suggestions were tailored to where you were, how cold it was outside, and the time of the day. But of course, we would love it, like I had said earlier, if you remember these suggestions later on, maybe even another day, and utilize them. So one can, the paper that's listed earlier in the slides, I don't know if I can get to it. Let me just go to it here. There it is. If you go to the Journal of American Statistical Association, or my website, actually, you'll get a link to it. That paper also gives you the method for looking at delayed effects. So, for example, I could imagine that if I give you a suggestion today, I might, in the morning, perhaps later in the day, versus not getting a suggestion, maybe later in the day, I might see use of that suggestion, and maybe even multiple times. So I could compare getting a suggestion now and not getting any more suggestions over the next 3 hours versus not getting a suggestion now and not getting any more suggestions over the next 3 hours. And that would be like a delayed effect because it would be over the next 3 hours. Some of the interventions we're involved with are more on the daily level. So there you could imagine that maybe if an intervention provided in the evening might have an impact over more than one day as opposed to just the following day. And again, one can use very similar methods to what we have here. You do have to do some weighting, but very similar methods to look at these delayed effects. And we would just love it if we could get delayed effects. The one thing, though, is we haven't developed a sample size calculator if your primary analysis would concern a delayed effect. We don't have a sample size calculator for that. Our sample size calculators are focused on these immediate effects.
Okay, great. The next question, thanks for the great talk, says Alex. How would you analyze categorical outcome data for micro-randomized trials? For example, did a participant take a medication or not, relapse or not?
This is great, huh? Yeah. So we actually worked on a project, and it was all about whether people would engage or not. That is, in this particular case, it was a we were providing engagement strategies. We randomized the engagement strategies, and we wanted to see whether or not, as a result of the engagement strategy, they would then engage with the app. So it was a binary outcome, like you're indicating. And we developed a method which has some similarity to the method here for exactly that setting. We're in the process right now of writing that workup, but it is very similar. One does have to be careful, again, because of the causal inference issues. But we have now quite a few studies where the outcome is binary. So we're trying to keep people engaged in self-monitoring, or we're trying to keep people engaged in answering self-report questions so that we can continue to collect data on them. In all of these cases, we have binary outcomes. Now, as far as, did Alex, it was Alex, right?
Mm-hmm.
Did Alex ask about categorical outcomes as well? Yes. And there, we haven't even gone there. And I think that would be really interesting to see how one could develop methods for categorical or ordinal, order categories. That would be also really interesting.
Okay, thanks. The next question, a very important clarification question. So the randomization occurs at the patient level, but the treatment estimates are averaged over all patients. Is this correct?
Right. So actually, even in regular clinical trials, we randomize at the patient level, right? Every person that comes in gets randomized to, let's say it's a 2-group trial for simplicity. They get randomized to be in one treatment group versus another. So the randomization occurs at that level for that person. And then we analyze, we compare the 2 groups. Here, this is as if it's a sequential randomization. Sequential, in our case, is actually a factorial design, because even though I didn't show you, let me show you that schematic. Oops, there it is. There was actually 2 treatment factors that were being randomized in time, both within a person, one in the evening, that's the lower green circle, and then the activity suggestions, that's the upper green circle. So these are factorial designs, and the randomization occurs within a person. However, our analyses, I have to be really clear about this, the kind of analyses we're talking about here, we're not targeting individual level effects. We're very much in the classical world. So the way we get close to the individual is by including more and more potential moderators. And if we want to size a study for a large number of moderators, we would need more people. And this is part of the reason why we're looking at it from this point of view, is because one does get these decreasing treatment effects and these feedback loops. People become less available with time. These are not settings where there's no delayed effects or no carryover effects in any sense of the word. That's not something that's going on in this particular setting.
Okay. Next question. In an MRT, only some of the mobile intervention components are randomized. Why do this, and what are the implications? In Heart Steps, actually, we had the 2 components that you see on this slide. So one was the activity suggestions, and then the bottom component was planning your activity for the next day. But there was another component in Heart Steps, and that was self-monitoring, where you could go at any given time to the app, and you would see the pattern of your physical activity across the day, across the week. And we had decided a priori that we wanted to include that no matter what. We weren't going to experiment with it. So it's always that situation in all of these studies is there's always some components you don't experiment with and other components you do. And you have to decide,
which components have the potential for having really negative effects. In this case, burden, habituation. Those are the components that you're more likely to experiment with, because you want to be really careful to provide them in a context in which they're most effective. Oh, by the way, in hypothesis generating analyses of those activity messages, we found that location made a difference. Now, we didn't pre-specify that, but it was that kind of, the current context, whether or not you were home or work, made a difference it appears to make a difference in how responsive people were to the activity suggestions. But that was a hypothesis generating analysis, and I didn't include it here. Again, though, I got off track there, didn't I? But there's always components that you experiment with, and there's always components you don't. Another thing we didn't experiment with here is the content of these messages was contextually tailored to whether or not you were at home or work, and the weather outside. We didn't experiment with that either. They were always, if you got a message, it was contextually tailored. Not stop, full stop. That was just the way it was. And it's always like that. You got to decide, what do you really need? To me, the things I want to experiment with are the components of the intervention which might have iatrogenic effects, or may be costly to maintain or produce to begin with. Those are the components I really need to get my act together on. And those are the ones I tend to focus my... in other studies, actually, we've also randomized components that were testing certain behavioral theories. So that would be another reason why you might randomize a particular component of an intervention, is because you have a theory that you want to test. That would make a lot of sense in that case as well. Yeah.
Okay. Next question. You talked about randomization probabilities and whether or not they're constant. In what cases would you want MRT randomization probabilities to change according to time-varying information on each participant?
Yeah, so as I mentioned in the HeartSteps V2, we are going to have the randomization probabilities be an output of an algorithm. We're working hard to make that algorithm back off when there's signs of habituation to that tailored activity messages. And the whole idea is to allow people to dishabituate to the messages, so that then the algorithm can increase the probability again as people become more, as people become more responsive, and then they'll be effective again. So we'll see if we're successful in that. We have another study called Sense to Stop. It's in the field right now. It's part of an enormous consortium. And there was a classifier. It involves a lot of wearables. And the wearables are used to produce a classification of whether or not someone is stressed each minute. In that study, it had to do with helping people quit smoking. And there's a lot of theory, behavioral theory, that says one of the risk factors for relapse to smoking is stress, because many people use smoking as a way to manage their stress. They try and quit, and all of a sudden you've taken away one of their critical tools they use to manage stress. So what we do in that study is we train people on how to use mindfulness exercises. And the intervention in that case is a reminder to access the mindfulness exercises. We conjectured that these mindfulness, a group of us conjectured that the mindfulness exercises would be most effective at times that the person is currently classified as stressed. Another group of us felt like, no, we feel like the mindfulness exercises would be most effective at times that people are not classified as stressed, because they would have more cognitive ability to take advantage of the mindfulness exercise. So for that reason, in that study, every day, around 1.5 times when a person is classified as stressed, they should get a reminder to practice their mindfulness exercises. And around 1.5 times when they're not classified as stressed, they should get a reminder to practice their mindfulness exercises. So that sounds all fine and good, but it turns out that people don't get stressed all that much. I was quite surprised about this. In fact, most of the time we're not stressed. So if you really want to pick up the stress times, you have to monitor people continuously. And then when you see someone who's currently classified as stressed, the randomization problem for that time has to take into account how many more times throughout the day they're likely to be stressed. If they're not going to be stressed very much in the remaining part of the day, then you want to randomize them with a higher probability to a treatment. But if they're likely to be stressed multiple times in the day, then you don't want to randomize them with a very high probability. So that's a setting in which we're using an algorithm to determine those randomization probabilities. And this algorithm, what it does is it forecasts for the remaining part of the day how many more times the person is likely to be stressed. And it uses that to form the randomization probabilities. So when we get that data, we will not be able to use GEEPAC. We'll have to use a method akin to the method Danny coded.
Okay, great. Yeah. Another question related to randomization probabilities. So when you're choosing them before you run an MRT, what are some guidelines for choosing those randomization probabilities?
Well, one is like the way we were talking earlier is about whether or not you want to induce dishabituation and so on. But in our setting, they almost always have to do with considerations of burden. Usually the team gets together and we think, well, on average, around how many times do you think it would be appropriate per day or per week to for the mobile device to interrupt the person in their life and suggest some sort of intervention to help that person. So we know that if we interrupt them too much, they'll disengage. So we get together and we decide, for example, in heart steps, we thought, well, on average, around 2 times a day. And since to stop, it was around, on average, 3 times a day. And this guides, with every study we've been a part of, we've had that kind of a discussion, and then that guides the randomization probabilities. There's always this constraint or budget on how many times we might interrupt the person per day, and that guides it.
Okay. And I have one more question here. So what is an example of an instance where an MRT would be used to provide data regarding the lagged effects of treatments?
Yeah, so there, the MRT would look just like the ones we have here, but you would, if your primary analysis is about a lagged effect, you would need a lot more people, because a lagged effect is you're going to have a much lower signal to noise ratio. So I probably would only do that in a setting where I had some behavioral theory that I'm trying to test. And I could see this happening eventually, because as we see more MRTs and behavioral theories become more and more dynamically nuanced, I could see that we could end up with some theories that might be about how, say, you provide an intervention and there's a delay initially, and then the person acts on it. And there may be theories about that delay and so on. It could be really interesting. But at this time, we're not really in that setting.
Okay, great.
Thank you.
Yeah, thanks for attending this one-on-one, and you can check the Methodology Center's website. We'll post a link to the video and as well as a copy of Susan's slides.
Yeah, I'll fix that error term in my slides before it gets put out.
Right.
Thank you.
Okay, great. Thank you.
Bye-bye.
Bye.